random forest. Decision trees are easy to develop, understand, and interpret. However, there is only one main problem that makes them not that ideal of a predictive method: inaccuracy. Despite the good and wonderful characteristics that decision trees have, such as easy to develop, understand, and interpret, when it comes to the prediction, they tend to overfit, and they tend to be susceptible to noises in training data. And that is unfortunate. Luckily, there is a method to overcome this problem, and that's actually a new method, kind of new method. It's called random forest. Random forest is an example of ensemble methods. Random forest is a combination of multiple independent decision trees. Each decision tree classifies its own way. At the end, the classification prediction is made based on the majority of votes. This tends to overcome the problem that decision trees have, and at the same time, keep the good parts of the algorithm. Ensemble methods. The idea of ensemble methods is to create an ensemble, meaning group, of machine learning algorithms and then make a prediction using an aggregation of the outcome of each individual algorithm. An ensemble of models is usually more powerful than any of its individual models acting alone. An ensemble of average algorithms, meaning algorithms with average performance, could make a more powerful model, meaning a model that has very powerful prediction performance. Random forest is an example of ensemble methods because it is a group of average performance decision trees. A random forest is an ensemble of trees, not just one single tree. One single decision tree is prone to overfitting. Many decision trees, aka a random forest, is more stable and is capable of better generalization. An ensemble of trees should be diverse. Therefore, we should introduce random variation when growing trees, hence random forest. How does a random forest work? To create and apply a random forest, you need to do the following steps. Step 1. Create a bootstrapped dataset. What is a bootstrapped dataset, you may ask? Well, it is just a recreation of your training dataset in a special manner. Basically, you randomly select different samples from your training dataset and set aside to build another dataset which is called Bootstrap dataset. But when you select randomly, you do not care what samples you have already selected. So you may end up selecting one or certain samples more than once. This is called sampling with replacement. Assume you have n samples in your training dataset. You want to choose a set of these samples, actually of size n, at random with replacement. You're going to use this dataset, which is called Bootstrap dataset, later to create and train decision trees. Since you are doing this with replacement, as I said earlier, some of your samples may be chosen more than once. So your Bootstrap dataset may not be actually all different samples, but a mix of samples that some of them are repeated more than once. The next step is to create trees using your Bootstrap dataset. You need to create multiple trees, hence a forest. Assume you have m features or independent variables in your data. When you create a tree, at each node of a tree, randomly select k less than m, features from your set of features. Then find the best split out of these k features to split that specific node. K here is a constant value. We're going to talk about this later more. When you create each tree, you need to let the tree grow to the largest extent possible. So there will be no pruning. Next step is to use all your trees, hence a forest, to make predictions. After growing a forest, you can make the final prediction by aggregating all the predictions made by each tree individually. Hence, majority of votes based on your tree. If you are dealing with a regression problem, rather a classification problem, then you need to use the average of prediction based on your trees, not the majority of votes. Let's now dive deeper into the previous steps, starting with the first step, which is make a bootstrap dataset. Suppose this is your training dataset. You have n samples of data, or n rows, and you have m features or m random variables which are in the column. The last column is the target variable. So you want to make a bootstrap dataset, which is every creation of this training dataset on the left. So it's going to have n samples, but the samples are going to be selected randomly, and not all of them will going to be different. So your bootstrap dataset is going to have the same number of features and target variable. But to select the samples, we're going to do it randomly. So let's randomly select one samples from the training dataset on the left. We selected sample number 3. So this is going to be the first sample in the Bootstrap dataset. Let's now select another random sample from the training dataset. Suppose we selected sample number 1. So this is going to be the second sample in our Bootstrap dataset. We're going to do this again. We select randomly sample number 2. We're going to put it after sample 1. And we're going to continue to do this, so on and so on. I'm going to do this one more. Suppose we selected sample 1 again. We put it here at the last row. So if you notice, because we were selecting these samples randomly, some of the samples that were already selected are selected again. Random selection with replacement will end in selecting repetitive samples. For example, here we have sample 1 here and sample 1 here. This is called samples with replacement. So this is our Bootstrap dataset. This is a regeneration or recreation of our training dataset on the left, but not necessarily all of the samples are different. Also, as you see here, the sequence of samples are different from what we had before. Step number 2, make decision trees. Use the Bootstrap dataset to make multiple trees, hence a forest. For each tree, randomly select a k subset of features and train the tree on the Bootstrap dataset. Remember that we have m features. So here we select randomly k number of features in which k is less than m. Let's see an example using our Bootstrap dataset. For the sake of this example, assume k is equal to 2. So the first step is to select two random features here. Suppose I select feature number 2 and feature number m. Then I make a decision tree here. This is the first node. On this node, I try it for feature number 2 and feature number m and see which of these two features give me the best split. Suppose it is the feature number 2 that gives me the best split. What do I do now is I disregard feature number 2 for future selection to make sure that I won't select it. Now, for the next split, I'm going to take another two features randomly. Suppose I take feature number I and feature number j. I try to see which one of these features give me the best split. Suppose it's feature number j. I use this feature to split my tree. And we do this over and over until we get a complete grown tree, which no further splitting is possible. So this is our first tree. We're going to continue this with another tree and another tree and another tree until we get a forest. After we have built our random forest, or should I say grown our forest, it's time to make predictions. To make a prediction on a given sample of data using your random forest, use each tree in your forest to make a prediction on the sample data and then take the majority of all trees' votes. It is important to remember when you are growing or building a random forest, the number of trees in your forest should be greater than the number of classes that you have. So let's see an example how this prediction would work. Consider our Bootstrap dataset that we had before. Assume that we get a new sample of data. So we know all the feature variables for this sample of data, but we don't know what target variable this would belong to. So basically, we want to use our random forest to classify this new sample. So what we do is we take every trees in our forest and run it through this new sample data to see what class they would classify it. So for example, the first tree classify this as class 1. The second tree classify this as class 2. We run it over and over for all the trees. Our last tree classified this as class 1. So we only see these three trees here, but the majority of votes suppose that is still class 1. So our prediction is this new sample is class 1. So we classify this sample as class 1. The thing that we did here is an aggregation of the solution that we have for multiple algorithms. Here, multiple algorithms are multiple trees. So basically, in random forest, we first made a bootstrap of data, and then an ensemble of different algorithms. Here, we use the ensemble of trees, and then we run all the algorithms on our sample data, and then take the majority of votes, which means aggregating the votes. This is called bagging. So bootstrapping the data and aggregating the result to make a prediction is called bagging. So using a random forest is an example of bagging. If you remember previously in our previous lectures, we mentioned one of the steps or one of the methods to overcome overfitting is bagging. Random forest is an example of bagging, which helps to overcome the problem of overfitting that a single tree would have. Evaluating random forests. If we use all our data to create a bootstrap dataset so that we later could build a random forest based on that, then how about a set of data for testing and evaluating the random forest? Well, we can use the unselected data samples left out to be in the Bootstrap dataset as test data to evaluate the performance of a random forest. These data are called out-of-bag dataset. Let's go back to our example. So this is our original samples of data that we have, and then based on that, we built the set of data on the right, which is the Bootstrap dataset. If you look closely at Bootstrap dataset, we have repeated samples. For example, at least here we have sample 1 being actually selected twice. So this means that some of the data in our original data in the left have not been selected or used in the Bootstrap dataset. For example, sample n has not been selected in our Bootstrap dataset. There are a lot of other samples that have not been selected if you consider a larger dataset with larger samples. So these samples that have not been selected to be included in the Bootstrap dataset is an example of out-of-bag dataset. We use out-of-bag dataset for evaluating the performance of random forest. We can then measure the accuracy of the random forest by the proportion of out-of-bag samples that are correctly classified by random forest. So imagine that we have p number of out-of-bag datasets. If we use our random forest to make a classification on these p number of samples out of bag dataset, suppose that out of this p, we have q of them to be correctly classified. That means that p minus q of them would going to be classified incorrectly or misclassified. Then the proportion of correct classification here is q divided by p. So this is a measures of accuracy for our random forest. The proportion of out-of-bag samples that are incorrectly classified is called out-of-bag error. So if we have p classes, if you have p samples of data out-of-bag dataset and our random forest classified correctly q of them, then p minus q of them were classified incorrectly. So this p minus q is the out-of-bag error. P minus q divided by p. How to build more accurate random forests? By repeating the whole process of random forest generation and evaluation with different values of k, we can generate and evaluate a bunch of random forests. Then we can pick the most accurate random forest. How to pick values for k? We can start by using a k equal to the square root of the number of features and then try to a few larger and smaller values than that. For example, if we have m features, then we start by k equal to the square root of m, and then we try k plus 1, k plus 2, and also k minus 1, k minus 2. Then we're going to evaluate our random forest, and we're going to pick the one that is most accurate of all. Let's take a look at the advantages and disadvantages of random forest. Starting with the advantages. Random forests are versatile and can be used for different applications, for both classification and for regression. Random forests can have excellent prediction performance on many problems. No careful normalization or extensive parameter tuning is needed for random forests. They can handle large sets of data. They can handle a mixture of feature types, both categorical and also numerical. For numerical, they can handle discrete and continuous. The disadvantages of random forests. Unlike a single tree, random forests are difficult to interpret. They may not be a good choice for problems with high dimensions. For example, text classification problems, compared to other methods such as linear models. Key parameters of random forest. The first one is the number of estimators, which is shown by n underscore estimators. This is the number of trees to use in an ensemble. The default is 10 trees. You should pick a larger number for larger data to avoid overfitting. The next one is maximum features. This is the K that we introduced. It has a strong impact on performance. It also influences the diversity of trees in the forest. Maximum depth. This controls the depth of each tree. The default value is 0. Number of jobs, which is shown by n underscore jobs. This controls how many cores to use in parallel computing.